First of all, I want to say, let's pull this down. I want to say that I updated the slides for the fourth time or something like that. Chapter 8, I finally put it up. I went to the eye doctor today, so I don't see so clearly. Here, silver shines. Told me I need reading glasses, which I kind of knew.
Sounds sad. Mark, she really knew what she told me.
I don't know, is there more cookie cupcakes for it?
There's one more.
I'll let her know. I'll take one for me.
I'm trying to show you this slide. I'm not going to go over it. You can go over it at home. It's on that same topic that we've been, apparently my favorite. Apparently, it's become my favorite topic. Here, look, this is this monster slide here I made.
Wow.
Where I go, the pictures are just to show you. In other words, I'm just showing you an example. 10-bit offset, 7 bits for the inner table, 47 bits for the outer table. This is an example. How I came to it. How I came to it is explained in this slide. This is the first stage is to say, well, if I have a 10-bit offset for if it's a 1 kilobyte page, then obviously you can have 10 bits for it, and that leaves me 54 bits if it's a 64-bit address. And then I work out how big the inner. I say if it's how big this, how many bits for here, and then all the other bits are here. Anyway, this is exactly what we did last class on the slide. I also changed, wait, did I change here anything? Maybe I changed something. This is the books example, which I changed a little bit, as far as the numbers here, 42 and 10. Well, this is a mistake, this should be 42. That 5 is, that's confusing. That should be obviously 42, just like this. I changed it. I was originally 45, I changed it. Anyway, yeah, that number's wrong. That's going to confuse you. I'll try to change that sometime. Okay, that's for your own enrichment afterward. Let's go back to chapter 9.
That was slide 48.
Oh, which exact slide was that? It's in the new one, 48. But 49, if you can note for yourselves that that's 40. That there shouldn't be any 2 to the 45th. It should be 2 to the 42nd, just like because it's this number here. Oh, maybe I'm wrong. Wait a second. No, that is right. I'm sorry. I'm reading it too fast. That is right. It's not a mistake. Take it back. That's right. Because the outer page table has 2 to the 42nd rows, but each row is 8 bytes long, which is 2 to the 3rd bytes. So we come from 2 to the 42. It's going to add 3 more bytes, 3 more digits. It is 45. So that's right. I'm not out of my mind. I've gone over that slide 4 times. I hope I didn't have a mistake in there. Okay. Remember, we're assuming always that, what are we assuming? That we're rounding up to powers of 3. My friend who works in this field told me that really you don't have to round up. You just do all kinds of mathematical computations and get the right number. Are those sugimans? What are those called?
Odds?
Odds, yeah.
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 They're from America.
I read an article that says they were very fashionable in like 2003, and now they've become again fashionable.
Really? They like went out and went back in?
Yeah.
Interesting. You know, it's like a lot of those styles though. The Harry Potter classes, like.
Back again?
Yeah.
I mean, glasses haven't gotten as big as my parents' time. They had really ugly
Which?
glasses. My parents, they had these
Really?
ginormous
Yeah.
glasses.
Okay, everyone's left here because they have to wash their hands from eating Ellie Shepard's cupcakes. But that'll give me time to close this and open chapter 9 and find the right page. So how do you remember where we were?
Yeah, we were in that chart of virtual memory larger than physical memory.
This one.
Yeah.
And I had shown how I had improved this chart.
Yeah.
I improved this chart by saying.
Okay, you wrote over it.
Yeah, I said like if this one is obviously not in memory, it means I got to go fetch it from memory. That's what this means. In other words, I'm coming here to here's my virtual memory, which is a large size. My physical memory is smaller, as you can see graphically. And this is, he calls it a memory map. I'm gonna call it like, it's kind of our page table. And that tells me where a page is in memory, but it also tells me if it's not in memory. It doesn't just tell me where it is in physical memory, it also tells me if it's not in memory. So we have two concepts, actually. We have something called invalid, right? We talked about invalid. What did invalid mean? Invalid meant
It's not.
that it's not my memory. I'm not allowed to go there. This is not the same thing. Now,
I heard it caused
I'm ignoring.
walkout.
I'm just talking. You can come in and out, and I'm talking to Elisheva and Gabriella and you're but
I'm Batsio.
you're Batsion.
Yeah.
Batsion.
So it's Leora. Yeah.
Liora. You're Batsion.
Yeah.
Not Batsion.
No, not Batsio.
I once had. I mean, Batsion is a very nice name.
But it's so
from
long. It's like Batsio is already.
You're the daughter of Zion.
Batsion is a very nice name. No, it's
With an
it's
A
from the
in it.
Haftarah, right?
Yeah.
I need to marry a
It's
guy
like a
named
bunch of
Boaz
places. It's also
because
like
I'm
Avola.
I'm no me
Yeah.
and
No, but
you
it's,
said that on my
I once
kids.
had a neighbor who's named, because there's Ben Sion, so you're Batsion. So she was named Rubat. Like
What?
Ruben, like Ruben.
Interesting.
Oh, I don't like that, no.
I didn't like that.
Very interesting.
Rubat.
But you know
far.
what, that's, yeah. I mean, like, at least my name is like biblical, you know, like,
Yeah,
that's
yeah.
just like
Made
made
up.
up. I don't know.
Yes, my kid, one of my kids is Mishael,
I just
who's appears in the Chumash.
Oh, yeah, Hanania or something.
No, it appears in later prophets, in like Ezra and Nehemiah, or
Right.
in Daniel. It appears in Daniel, but it also appears in Chumash.
Oh.
People don't know.
I know.
Nadav and Avihu were drawn out from when they died. Right, they died in the Aish
Yes.
from Hashem, and they were dragged out, their dead bodies, by Mishael and I forget who the other.
There was Hanania, Azariah,
They're like the
Mishael,
cousins. The
and-
cousins.
Yeah.
What?
There were Hanania, Azariah, and Mishael were from Daniel.
From Daniel. From Daniel.
Yes.
But and I have another boy named Lavi, who's also
Yeah, I
a
have a
bit.
nephew named Loki.
You have a what?
A nephew.
A nephew.
Loki.
No,
Lavi.
what?
It's also a biblical word. It's not a biblical name, but it's a biblical
Right.
word.
How do you spell it?
Lavi?
Yeah.
Lavi.
No, but that's Levi.
No, L-A, not L-E.
But in Hebrew, how's
I spell it, in Lavi it's Lamed Bet Yud Aleph.
Oh,
Oh,
okay, that's
that.
Oh,
It means
okay.
lion.
Okay,
It's lion. Lamed Bet.
It's like Liva before a girl.
No, it's like Aryeh,
Yeah.
lion.
It's yeah, it's
Like, as in.
No,
give-
do you know what you guys say for us?
The
It's
words
Lamed
for
Bet.
lion in
Yeah,
Hebrew are
Aleph.
fear,
Oh, Olive.
gur, Aryeh, fear, shagal, I think. Yeah, and Aryeh. Okay, so we explained there's two invalid bits in a sense. One is saying, well, wait a second, I don't have access to that memory. It's not my memory, it's somebody else's. Another is saying, oh, it is your memory, but it's actually not mapped to the physical memory yet. It's in the disk. Because we're talking about this new topic, which is really called virtual memory, which is saying that the memory is not even in the physical memory, it's on the disk. We've added this new part to the picture. It's a bit confusing because it's similar to what we've done before. I don't know what the point of this slide is, but you all know this picture by heart by now, right? Stack, heap, they each grow. I guess part of what it's trying to say here is that you can make your memory larger as you need it to be, as you need. As you don't have to say, I've only got this amount of memory. If you have this dynamic memory allocation, somebody says new, in their program, give me 10 million bytes. So I go to I can give it to him because I have a disk here. I can use disk space. So this is the virtual address space. Now, virtually, it seems like I've got all this space, but some of it might be actually on the disk. Here, let's see what he says here. This should be the, not he. The space or hole between the growing heap and growing stack will not require physical memory until assigned. In other words, my stack has so far gotten down this far, and my heap has gotten up this far, and there's this empty space here that I haven't yet used. If we would have like a normal contiguous memory allocation, I have to have space for that allocated, even though I'm not using it yet. What we're saying here is, since everything is virtual, it means everything can be swapped out to the disk. I can create it as needed. Enables sparse address spaces with holes left for growth. Dynamically linked libraries. Also, I can have dynamically linked libraries. In other words, sparse means that there's gaps in my address space. Obviously, system libraries can be shared by a mapping into several virtual address spaces. In other words, I can have my system library that two functions are using at the same time. It both be in there, each of their, I want to put in memory once, and it's in each of their virtual memories. That was the same we saw with paging. We did it with paging too. Shared memory by mapping pages into several virtual address spaces. Right. You could also share memory between two processes, because just like the same thing is true with paging. Right? In paging, I can have pages between two different processes theoretically. And here I can have I have my whole virtual space can be between two different processes. Pages can be shared during fork. Speeding process creation. One of this, when we do we talked about forks. Did we talk about forks in the lab?
Yeah.
When we made a fork. Remember, a fork is a function call, a library call that creates a new process, a child process. And this can be very slow. This is a major problem. You create a child and you have to build his process control block, you have to allocate memory, you have all these things. It can be slow. Pages can be shared during fork. So in other words, when I can get the process up and running by letting him use shared, letting him use the code section, for example, of the parent, right? The child and the parent share the same code. So I don't have to create a copy of the code, I don't have to copy all that data. I can just let them share it. If I wouldn't have paging or virtual memory, then I would be forced to create a whole new code section with this. Remember, we had an offset bit that says the beginning, where a base register and an offset register. We had to say it was contiguous. I would have to create a copy, all the code. Here I don't have to. I can share it, and then we're going to talk about. I think we're going to talk about it a little bit later. Where is it? Oh. Or we already talked about it. Copy on. Remember we talked about that cow. Copy on write. Even if it's even the written data I could share until I actually have to write to it. Okay, shared library using virtual. So here's just a graphic representation of the shared library is somewhere in memory, somewhere between the stack and the heap, let's say. And I can have actually the shared pages in the virtual, this is the physical. In the virtual space, each one thinks he has a copy of the shared library, but really they're on shared pages between the two of them. In other words, the library function is only once in memory, but it's in two virtual spaces for two different processes. Okay, now we're going to talk about a major topic, which we're going to spend a lot of time on, which is called demand paging. And we can say, wait a second, we already learned about paging? We learned about paging in the sense you can page the memory. But now we're talking about, it really shouldn't be called demand paging. It really should be called demand framing, really. What we mean by demand paging is that a process, let's go back to this picture. A process is, this is page 0, page 1, and page 2. Demand paging would mean that whenever I need a page, let's talk about pure demand paging. Pure demand paging means I start the process off with like no pages in memory. And the first request for some data to read the first line of the code says, wait a second, I don't have that page in memory. Grab it from disk, key point, from the disk. It's not in memory at all. And put it into physical memory, map it, give it and then I can use it. Whenever I need the next, and then I'll read all the information on that page. When I finally get to the end, if my code is going through line by line, I finally got to the end of that page, I need the next page. Oh, I have what's called a page fault. Page fault, I don't have the page in memory, grab it from the hard drive, bring it in again. And what's going on is like every time I need a page to be read, I'm gonna have a page fault and I'm gonna bring it in from outside. Okay, so that was my summary of it. Let's see what the slide says. We could bring an entire, all right, so I wrote this. we could bring theoretically, we could bring an entire program from disk into memory at load time. Just load up the whole program into memory. But instead, we'll bring a part of the program, enough to fill a page or several pages of memory. Well, maybe this is not pure demand paging. When I was describing pure, we have nothing. Here is not pure demand paging, but we'll say the first page of the program will bring into memory no matter what. Or maybe the first 3 pages, and I say we'll make a guess. That's called paging. Demand, and then, but still, that's not going to be good enough. We have 2 or 3 pages. Additional page. Additional page size pieces will be brought in only when they're needed. Like I was saying, all of a sudden I get to line 100 in my code. I need line 101. It's not in the page. I'm going to have to grab a new page from the disk. So why is this good? Well, yeah, less I/O. This is a funny use of the word I/O here. What we mean by I/O here is we mean copying from the disk of memory. In other words, every program, if you think about it, are you guys with me? Yeah? I feel like everybody is looking at their phone. Except for Betsy.
My phone's not in my hand.
Oh, you're looking at your
I'm
type.
writing notes.
You're writing notes. Sorry. Yeah, I know. Well, that's why I want you to tell me. I'm just writing notes. Then I forget. If you're writing notes, great. If you're writing in TikTok or whatever, that's okay. Can you write up TikTok? I don't. I feel like I'm very modern because I joined Instagram, but TikTok, I'm not yet there. I won't.
I'm not on TikTok either. I mean,
Okay.
I'm TikTok. Yeah, you know I'm very modern.
But I don't even use it. I was on Facebook, and when Facebook first came out. I've been on, but I never log in anymore. I thought at a certain point I realized that it's for old people, so I stopped using
I
it.
use
But then in the meantime, it became
Wow,
popular.
you're old.
But it's like a fashion. It's like the same thing with dog food. It came back again about 8 years ago.
I don't have Instagram. I
What?
don't
But she's wearing
Oh,
Ugg boots. So, I don't know what they're called. No, like Ugg boots that go in and out of fashion. So I just was saying that Facebook was out of fashion, in fashion, out. Anyway.
It has great groups that help women make up.
Yeah, there are useful things. I should probably be on.
I don't use Facebook.
I don't have any-
Marketplace.
I don't- It's really because I have children. I'm not that busy. I'm not.
Facebook Marketplace is amazing.
Anyway,
That's all I do.
so why do we say less I/O needed, no unnecessary I/O? Because it could be that you run the program and you load the whole program up into memory, and then the program uses 3 lines, and then the guy says quit, and you exit. And it could be that the program never actually used all of its, but meanwhile it took a long time to load up. It's like sometimes like you loading up a program takes time. You got to copy all the data from the hard drive into memory. That takes time. If I just copy the first 2 pages of the program or first 10 pages of the program, then I have my program up and running quickly. And only if I need those pages will I actually have to load them. So that's what we mean less I/O needed. No unnecessary I/O. In I/O we mean copying of data from the disk to memory, which always happens, right? Less memory needed. Also, I don't need so much memory because it could be that these are the advantages. Less memory needed because it could be I'll only use the first 3 pages and I won't use the rest of the program. Faster response. Well, obviously faster response. The program will be loaded up and running quicker. I'll get a quick response. I'll quickly be able to more users. I'll be able to have more users or more processes running. If I have less memory needed for each process, then I can squeeze in more processes. Obviously. Page is needed. Reference to it. So here's this is the key point. Remember I said you need 2 bits. This kind of describes that idea of 2 bits. Because say either it's an invalid reference. That's the valid bit that we talked about before. You're trying to get to an invalid location. You're trying to add to memory that you weren't even supposed to even right. You weren't allowed to go to that memory space even, let's say, in virtual. Well, you're trying to go to an invalid page. Page that's not yours. So abort. But now, what if it is your page? It's just not in memory. So bring it into memory from the disk. So we have to know, we have to have some kind of data about every page. Whose is it, and is it in memory or not in memory? Now we have something called a lazy swap. Swapping is this process. Well, to really explain swapping properly, the best way to think about it is like this: that let's say all the memory, let's say I've got 10 programs running in my here's my picture. I got 10, here's my physical memory, and I've got 10 programs running. Let's say it's not, instead of being blue and gray, let's say it's all blue. I got 10 different programs, and then all the physical memory is full. And now I say, I need a new page. I have a page fault. Page fault means I need a new page. I have to swap somebody out or swap somebody in. In fact, I could, there's two choices I have. One is I could just swap a single page out. Another possibility is I could swap an entire program out. I can say this program, I'm swapping it back to this. And I think that's actually what they mean at first. We'll talk about page, but well, no. So we're talking about social life. We're not talking about entire program. Page. Lazy swapper never swaps a page into memory unless the page will be needed. So that's kind of like what I was explaining before of a pure demand paging. In other words, only bring in a page. You don't bring in 3 or 4 pages at the beginning. You just bring in nothing. And only when there's the first fault you bring in it. That would be a very lazy swapper. Swapper, as we just I also go with pure demand paging. Pure demand paging because it's I'm never getting a page unless it's demanded. That would be pure. Demand paging in general just means I give pages when they're demanded. But it could be that I give the first few pages even before they're demanded. Swappers, as we discussed in earlier chapter, swaps out the whole program. That's what I was saying. We did talk about swappers before. If you remember, we talked in a previous chapter, we talked about swapping a whole program out of memory because we wanted to bring somebody else we wanted to let somebody else run. We had too many programs running maybe, so we wanted to make memory, so we swapped the whole program out. Now we're talking about swapping in and out just pages, which is better. You don't have to take the whole program out. A swapper that deals with pages shouldn't really be called a swapper. It should be called a pager. So it's correctly called a pager, but it's sometimes in computers you have lots of terms that are people use the old term for the new thing sometimes. That's so some people will call it a swapper. It's really a pager. Swapper technically is referring to what? The swapping out of the whole program. Okay, so but we still like that word. It's a nice word, swapping, because paging doesn't mean, we don't know what that means. Maybe paging means dividing the memory. But so we're going to use the word swapping. Transfer a page of memory to contiguous disk space. So here's our disk. Here's program A. So here you see swapping out a whole program. Actually. Look, we take program A, and we swap out all of its pages to someplace on disk. And then we can swap in some other program. Okay, that would be a total swap. So now let's talk about these invalid bits. So with each page table entry, a valid invalid bit is associated. But this is the different valid invalid bit that we saw. Okay, right? I made this point a couple times already. This is the valid bit to say valid means in memory. V equals in memory, or also called memory resident. It's residing in the memory. I, invalid, means not in memory. But it doesn't mean that it's an invalid location. That would be a different bit we have to have. Initially, valid invalid bits are set to invalid on all entries. So that means here would be a snapshot after a certain amount of time, a bunch of pages are valid and a bunch of pages are still invalid. But at the beginning, we might set them all to invalid. During an address translation, if valid invalid bit in the page table entry is invalid, then we call that a page fault. I said that already. That's a page fault. That means it's not in memory. If it would be pure demand paging, we would have them all set to I, we'd have nothing in memory. The first memory read would cause a page fault. Page table when some pages are not in memory. So here you see valid, invalid, and when it's got a number here, obviously it's valid. You could have a number here and it'd be invalid. I don't know why they didn't draw it that way. Why would there be a number there if it's invalid? It'd be because it would be garbage from some other moment in time, right? It could be that from a previous memory. Memory is not always all zeros. I mean, there's no such thing as blank memory, right? You guys know there's no such thing as blank data. It's either zeros or garbage or something useful. It can't ever be just, it's not there. So that's why this picture is a little bit weird. It could either be zeros or garbage. It's really garbage. So that's why I have to have, because you can say, I don't need the valid bit. I'll just look wherever there's a number, then I know it's valid. Why do I need to also say it's valid? Just wherever there's a number. The answer is because there's numbers everywhere. There's really obviously some kind of number here. It's just a garbage number. So we need that valid bit. And this tells me frame. Remember we use the distinction between frame and page. Frame is when it's in physical memory. So frame 4, so page 0. Wait, let's look at this here. In the logical memory, page A is the page I want. But I'm gonna go, if I want page A, I'm gonna go to this thing, I'm gonna go to this page table, go to index 0, that's what I want. And I'm gonna see 4. What does 4 mean? 4 means that that's where I'm gonna find A. Oh, there's A in memory at page 4. If I want B, well, I'm gonna come here and see B is supposed to be at place 1. So I'm gonna go here and see, oh, invalid. And I'm gonna now have to go grab it from the disk. And you say, wait a second, how do I get it from the disk? What are we obviously gonna have some additional mapping to locate it on the disk. I'm gonna have to, which is not written here. I'm gonna have to have some additional information in the operating system about where it is in the disk. It's not written in this diagram, but it has to be, right? You can't just magically go grab B without knowing where it is. So it's not drawn in this picture, but there's an additional piece of information either in the page table or somewhere else. So we'll get to more details. If there is, so it's not just in saying words what I just said. If there is a reference to a page, first reference to that page will trap the operating system called a page fault. Operating system looks at another table to decide if it's invalid, which they support, or just not in memory. So you see, there's another table. See how he says that? Another table. He didn't draw it. But there's another table to tell us, this invalid just told us that it's not in memory. Now we say invalid, we're going to go to some other table, and that's going to tell us whether that is a legal address or a legal one. We just have to go get it in memory, and if it's go get it in the disk, and if it's legal, it's on the disk. So we have to know where on the disk. So the table will say where it's on the disk. If just not in memory, get an empty frame from the disk. In other words, find. When you say get, what do you mean get an empty frame from the disk? We have a list of free frames. The operating system maintains a list of all the free frames. It'll choose one of them, and that's what it means get empty free frame. Swap the page into the frame by a scheduled disk operation. So request a disk operation, which is obviously slow, and it's going to copy that frame into actual memory. Or it's going to copy that page from the disk into the frame that we found. Now you have to reset the tables to indicate the page now in memories. Set the valid bit to V, valid. Right? We have to say now it's valid. Now we put it in. And now we can finally restart the instruction that caused the page fault, and this time we won't have a page fault because it'll be in memory. This is just showing you all the steps that I have to go through. It's like an algorithm, right? Okay. Oh, so here I mentioned.
Can I ask a question about the diagram and picture? If, like, for example, A is in physical memory, then it's not in the disk?
No, we deleted it from the disk.
It's not deleted, it's just.
We're not going to delete it from the disk. We're going to copy it from the disk because, right, when you run your Word program, it's still on the disk.
Okay.
You just brought it into memory. Because you know why? I mean, you could say we'll take it off the disk. I mean, first of all, because we know that when we're finished running, we're going to have to copy it back. And copy takes a long time. So we'll just save ourselves that effort and leave it there. So yeah, it'll always be, that's going to be a crucial point though, because well, we'll see, we talked about the dirty bit. Anyway, it's going to become, it's a crucial point because sometimes we're going to copy things back. What if we changed it?
Right.
What if we change A? We could have a situation where A is different from A because we changed it a little bit, which is legal. So now we're going to have to keep track of whether we changed it. We call that, we'll get to that. We call that being dirty. If this data is dirty, data being dirty means that it's no longer reflecting what it's supposed to reflect. It's been messed up. So we'll see. We'll talk about that. So extreme case, start the process with no page. I mentioned this before. With no pages in memory, the operating system sets the instruction pointer to the first instruction of the process. So we're already at the first line of the program, and it's not there. Non-memory resident, we get a page fault, and then we have to go load the page up, and then we'll restart the process and run it again. And for every other process pages, on the first axis, I don't know what I meant. No, for every time the process accesses a new page, on the first time it accesses something from that page, we have to bring in the whole page. Actually, a given instruction could access multiple pages. Oh, multiple page faults on one, right? Can you imagine that? You could have a multiple page fault on a single load word. Well, load word is hard to imagine because you're just loading from one place in memory and putting it into a register. So why would that?
But a load word is 4 bytes, as opposed to doing a load byte. So that might not have. So
no, because a load word is always going to be on a word boundary, and word boundaries are multiples of 4, and pages are multiples of 4. You'll never have a word that stretches over between 2 pages.
So is there a command that's like a load of a
There are on some, so this is the thing. We only learned RISC. We only learned reduced instruction set assembly. But there's assemblies on other machines that are kind of complicated things. Instead of load word to, what would it be? Instead of load word to, what's it called? On a register, we can have a new load word to a word, to a location in memory. Load, copy some data from memory location A to memory location B. In other words, we never saw a command like that, but such a command do exist. You with me, Batsio?
Yeah, I'm looking at the slides on my phone.
You'll get the slides?
On my phone,
Oh.
because sometimes it like switches.
Yeah. So you understand what I'm saying? You could have a load word, but not a load word, but a copy word between 2 different memory locations, and then you could have 2 page faults. Okay. But the pain is decreased because of something called locality of reference.
What is pain?
The pain, I mean to say, the problem of having to upload having 2 page faults simultaneously. We're always trying to minimize, here we're calling it pain, minimize trouble, difficulty. The amount of difficulty we're going to have to do the copying stuff is going to be less because something called locality of reference. What is locality of reference? Anyone want to guess what locality of reference is?
How close something is in memory to where you are? How
Yeah.
far you have to reach to get it?
Yes. It's basically, it's like a program will generally, most of its references are near the other references. As it progresses, it may refer to things further away, but only once it gets there. It's kind of like you live in an apartment on, Sapporo Street, so you go to the McCullough near Sapporo Street, you go to the hairdresser near Sapporo Street. Everything you do is around where you live. Occasionally you go to a faraway place. So programs are the same way. Most of their memory accessing is in a constricted area, close to their code. Okay. Hardware support needed for demand paging. We need to use some hardware support for this. We need a page table with the invalid bit. We need obviously a hard disk with designated swap space. See, that's the thing. You can't just, this swap space has to be designated. In other words, it's on the disk, so it's where your programs are. But it's not, we don't want to like write, we have to have space that we know is not, nobody's going to write put a program there. It's essentially set aside as memory on your hard disk. It's given for now the operating system has to have some kind of footprint. That's his place. We call that swap space. It used to be when you installed Windows. Nowadays, you install Windows, you just say yes, yes, yes. But it used to be when you install Windows, it would ask you how much swap space do you want, and it was always a question: how much? Like the more you give it, the better, or maybe not. And sometimes they'd say no. If you have enough memory, give it a very small swap space because you don't want it to be swapping too much, because the swapping is slower than just having everything in memory. On the other hand, it allows you to run more programs and run bigger. So if you have enough memory, you don't really need swap space. But if you, in fact, my wife is actually saying that in her company, they had I think it was her idea actually. They needed a huge amount of memory for a program. And to get a server that would have that much memory was very expensive. So they got, a server where they rent the server for like an hour or for a day. It's all on the cloud. So they instead configured the server differently. They got a different server, a cheaper server with less memory, and just made a lot of swap space. Most nowadays people don't use swap space so much, but she was just using it a couple of weeks ago because it enabled. They need to run something one time, and then they were going to get rid of the server. They bought from Amazon, a temporary server on the cloud with a very large swap space and smaller memory, so it was cheaper. So you need to have that. So that's hardware in a sense because you need a disk. Instruction.
Time, right?
What?
Swap space takes more time, like swap.
Yes, using swap takes more time because if everything's in memory, that's ideal. Really ideal with everything in cache. But all right, instruction restart capability. You need some ability to be able to go back to the previous instruction, and run it again. So that's also kind of hardware need. I'm not exactly sure about this first point, why the page table with the valid bit is hardware support, why that's in hardware. Well, if it's a transfer look-aside buffer, then it's hardware.
Wouldn't it be hardware just because it's a simple wire 01 or 01?
No, I don't know if that's, it could be hardware. I think the page table could be in memory and it could be in hardware. And obviously it's better for it to be in hardware, it'll be faster. And we talked about that when we talked about the TLB. The transfer look-aside buffer, that we store some of the page table in the TLB to make it faster. So now we're talking about problems with instruction restart. So consider a function. Remember I said you could have a copy word to word. You could also have another function in your assembly. Imagine an assembly language command that was copy this array of 1,000 bytes to this array of 1,000 bytes, or this array of 1,000,000 bytes to this array. So here, I'm jumping to point 2. I guess I'll go back to point 1. Consider an instruction that could access several different locations, like a block move. In other words, copy this huge array to here. In the above, the source and destination overlap. I'm saying copy everything from memory location 100 to memory location 50. But from 100 to 200, that's 100 bytes. And I say, now copy it to 50 to 150. So it's overlapping. So as he starts writing, he writes this one to here, and this one to here, and this one to here, eventually this one to here. And he starts writing all the data. At a certain point, he's written this one to here, right? He's written like this one, again, this one to here, let's say. So now what's happened? He has lost his data. He already wrote it, it's true. He already wrote everything that was in this overlapped area is already up here. So now he writes onto here. But if he restarts the command, then he'll go back to here and copy to here. But some of this stuff has been overwritten already by the stuff that was in this area. And so restarting your command, in other words, I could have a command that says, copy this huge area to this huge area. I do it. In the middle is a page break. So what's my procedure? We just saw the algorithm. My procedure is stop everything you're doing, bring in the page in memory, and restart the command from the beginning. Not from where I left the command. It's one command. Copy this area to that area. So I'm going to have to start the command again. But in the meantime, the data has been ruined. So starting, this is a problem point. It's restarting, that's what I said, problems with instruction restart. In the above, source and destination overlap. Some of the source data may have been overwritten when a page fault occurs. Simply restarting may not work. One solution is to determine if a page fault will occur before even starting the operation, but this is costly. In other words, calculate. When I do that command, wait a second, am I going to get a page fault? And if I am, then I'm going to pretend I got it right now before I even start and bring it into memory. But that's costly because I'm going to have to check it every command. I'm going to have to check, is there going to be a page fault? Is there going to be a page fault? There are other problems that need to be solved. A simple store, what did I write here in the beginning? A simple store word can be restarted if the store location is not in memory. A simple store word can be restarted. Right, if I'm just copying from a register to memory and it's not in, then that's no problem. But this could be a problem with a block. Okay. Here is a graphic representation of a page fault. Steps in handling a page fault, also called accessing an invalid page. So again, steps in handling a page fault. So let's start from the beginning. It's really, I don't know if it looks complicated, but it's not. Here's my command. My command is load to some register data M, yeah? Load M, that's what that means. It means do a load command. So first I do a reference, I go to the page table. If it tells me invalid, then I go to the operating system. It was an invalid page. Here, this invalid means not that it's an illegal location, but that it's, well, the operating system will decide. Is it invalid location or is it a page is on backing store? If it's page is on backing store, which is what we're trying to describe, then go find that page. The operating system will have to keep track of where those pages are.
Then can I ask a question?
Bring in the missing page and put it dafka in a free frame. Because I'm going to check, the operating system will check his list of free
Can't
frames.
hear us. Oh,
Then reset the
forgot about that.
right? I got to say, page table, you no longer are invalid, you're valid, and I'm going to put the number here. In this page table, I'm going to have to put the number of where this free frame in physical memory is. Where I put this no longer free frame. I'm going to have to write inside of this gray box the location in physical memory of this page. Now restart the instruction, 6. Go back and run the instruction again. Now it'll go to the page table and say it's valid. And it'll jump over here and get the data and everything is hunky-dory. Now this is a word description of what we just said, but a little bit more detailed. So let's go over that. Hi, Liara. Welcome. Trap to the operating system. So what did I write? Detailed description.
Someone asked a question in the Zoom chat.
Yeah, oh, I need to look. No. When I'm in this mode, it doesn't show me there.
It's the first.
Oh yeah, chat. So I would ignore it, it's red. Isn't there 2 valid bits? Yes, there are 2 valid. Why did you say that the operator decides if it's actually valid? Right, well, I'm just trying to explain the diagram. In other words, the diagram, I said, let's go back to slideshow. Yes, there are 2 invalid bits. Logically, there are 2 invalid bits. Where they actually are, it depends on your implementation. I could have written it here that it will say another bit here, but they wrote it this way. So that means that the operating system, so this is just telling me that that page is not valid. I'm gonna have to go over to the operating system is gonna have to keep track of some more information. And we listed that. It's gonna be whether the page is invalid in the sense that it's illegal for me to go there, or whether it's really just on the backing store. There's gonna have to be, that is another invalid bit that's gonna have to be over in the operating system is a program, right? He has arrays, linked lists. He's gonna have a linked list, and he's gonna have an item in that linked list called this process. And it's gonna keep track of all the pages for that process and whether they're, in other words, whether this page table is, where is this page table? What is this page table? Is this page table in memory? It could be. It could also be in the operating system. They just drew it over here. But it's really inside. Really, you could draw a bigger box with the operating system, put this inside there, and then have another sort of table that tells me whether it's on the backing store or it's invalid. And if it's on the backing store, where on the backing store it is. They didn't draw all the details, that's all. But the short answer to your question is, yes, there's another bit, they just didn't draw it all. But whether that bit is in the operating system in the sense that it's here, this page table may not necessarily be in the operating system. It could also be hardware, in which case we'd call it a TLB, which we learned about. Okay, trap to the operating system, that's this trap here. Save the user register and process state. Right, so we're gonna, determine the, yeah, it's complicated. You see, now they're making it a lot more complicated. Because saying this is really just an operating system fault, and we don't know why we got a fault. And it could be, so we're gonna save all the registers of the process and stop it. Maybe it's a fault because we're supposed to switch to another process. Maybe the process went to IO. Remember we learned about that? Maybe it's a scheduling issue. So we don't know what the trap is. So the first thing we're gonna do is save the user registers and process. Then we're gonna determine that the interrupt was not because of time limits or because it went to IO, but it was an interrupt because of a page fault. So then we're gonna check that the page reference was legal. And if it was legal, then determine the location of the page on the disk. Like I said, now we're going to issue a read from the disk to a free frame. Actually, it's missing a step. I could put it in 4.5. Find a free frame in your free frame list, right? You got to find a free frame. Then, wow, this would be really interesting if I would ask you this question. I wouldn't, but I mean, I could, but I would not expect you to be able to answer all 12 steps or even 13. The question would be, describe what happens when a page fault occurs. Describe the steps. I mean, it's a valid question to ask, but I wouldn't expect you to think of all these steps. But let's see what it is. So like I said, 4.5 would be find a free frame in your free frame list. Issue a read from the disk to that free frame. Wait in a queue for this device until the read request is serviced. In other words, I asked for something from the disk, but the disk could be in the middle of writing something to some other process, right? There are other processes. So I have to actually just put it in an IO queue. Remember we learned that, right? If IO queues. Maybe the IO is busy. The disk can't write to two different places at the same time. Then wait for the device seek and or latency time. It may take me time to, when I'm actually my turn, I'm gonna have to wait now until the disk actually finds my location. The seek or latency time we talked about is to find the thing on the disk. Then finally begin the transfer of the page to the free frame. All that is essentially getting the free frame into memory. Then while waiting, allocate the CPU to some other user. Because now we're essentially in an IO moment. We're copying data. So we're in an IO moment. So actually it was good that we saved those registers and process state, because when we're going to do this, allocate the CPU to some other process, he's going to overwrite the registers.
We are asked another question.
Yeah. This is exciting, right? What we're doing here. This is very exciting. Going through all the steps of the operating system. They are asked the question in where? In the chat?
I think on the Zoom. Sure.
On the Zoom. Oh. Yeah. Okay. Chat. Why did you say that you decide if it's actually? Oh, can you go over the diagram again? Yeah. Well, I'll keep going back to we determined that it was a page fault. We now made the kriya, we requested something to write from the disk to the right to the free frame. But this process number 4 takes time, is what I'm saying now. 4 takes time. And while it's doing that, the operating system shouldn't just, the CPU shouldn't just be sitting there idly by waiting for the disk to copy to the memory. So that's what the next slide says. While waiting, allocate the CPU to some other user. And that's why the user register and process state was saved to the operating system in some data structure. Now receive an interrupt from the disk. This is actually a very good review of the whole course, this little slide here, because it's telling you all the things that you sort of already should know. Receive an interrupt from the disk I/O subsystem that the I/O is complete. In other words, meanwhile, we let somebody else take the CPU. We're now waiting for an interrupt to occur to tell us that the I/O finished. He's written in memory. We can go back to that first process. Now, save the registers and the process state for the other user. That other guy that we started up, we got to bring him back, his registers, and copy them back into memory. What do we call that, by the way, when we do that? Save the registers and process state for the other user. What's that called? Context? Mm-hmm. Or at least that's part of the context. Yeah, that's context switching. In other words, copying that and allowing the new process to run. So we're doing a context switch. We're putting the other guy back in. Determine that the interrupt was from disk. Okay, so we got this interrupt, but we don't know what it was actually yet. We just know the interrupt just says operating system stop. And then you got to look at a table and see which blinking light is on. Exactly how that works is an interrupt table. We're not going to discuss it. But you're going to have to determine which interrupt it was. In fact, it was one from the disk. Correct the page table. So now we're back to this picture here. Correct the page table 5, which means put in this gray box the location of this free frame and mark this I as a V. So correct the page table and other tables to show the page now memory. Wait for the CPU to be allocated to this process again. Now the CPU has to actually find run this process. Restore the user registers. The CPU will do this job of putting in the registers from the operating system. Will use the CPU to copy all the data that it had copied out back into the registers and a new page table, and then resume the resume the interrupted instruction. That's what we see over here with this restart the instruction. And then we're back to 1 again. That's the restart actually. The 1 is again run the function. Okay, that was a mouthful. Okay, this effective access time we talked about in architecture, in computer architecture. And we've seen this same kind of mathematical thing we did before, right? Where did we see this before? Remember? Where we have p as a number from 0 to 1.
Oh, was this with one of the finding out the predictions, making the predictions of CPU burst?
Oh, no, not that. It's similar. You're right. That's also a number from 0 to 1. But this is different. This is different. I think it's another example that we did something similar to this. But that's a good point. This p is saying the page fault rate. How often we have a page fault? What % of the time? In other words, we'd like it to be that we don't have to do all of this huge process a lot. This is a time-consuming process. If we have to do this on every instruction, our program will run very slow. What kind of a page rate would we like? We'd like it to be 99% of the time that a memory request is in memory. And we only 1 in 100, for example, have to do a page fault. So this is just a way of saying, what is that page fault rate? If p is 1 or 99, let's say 0.99, then almost every reference is a fault. That would be bad. We'd like a p of 0. We'd like a p, like the rate of fault should be like 001. Should be as small as possible. So let's look at this picture here, EAT, effective access time, is equal to 1 minus this tiny number, no, this hopefully tiny number, 1 minus this tiny number, so about 1, hopefully, times the memory access. In other words, if it would be actually 0, we'd never have a page fault, then our effective access time would just be pretty much this memory access time. But it would just be the memory access time. Whatever the memory access is, how long does it take me to read a byte from memory, to read or a word from memory? That takes me a certain amount of time from memory. It's very quick, but it still takes some time. So hopefully if the P would be 0, we'd never have a page fault. It would be just, that would be it. And then this P would be 0, 0 times whatever is 0. That would get rid of it. But it's not going to be 0. It's going to be more like, what did I say? P should be 0.001, for example. So I'll say 0.01, 1% of the time. So it's going to be 1% P. P is 0.01 or 1%. Very small amount of time times what? The whole page fault overhead. I mean, that means everything that we discussed up to now, plus the swap of the page out, the swap of the page in, because presumably we're going to imagine a situation where there's no free frames. This was all describing, assuming there's a free frame. But imagine it's one, in other words, there's one more step in this 12 or 13, I think 13, because there's another one over here, 4.5, which was what? I forget. Did you write that down, Leora? What was 4.5? Oh, you're about to say it.
I was like,
Gonna get every time to make that mistake. Did you write that down? No.
which-
What was step 4.5?
Oh, I didn't write the numbers of the steps, but what was,
Check that the page reference was legal and determine the location of the page on
you had to
disk.
find the free frame.
Oh yeah, find the free frame. There you go. Find the free frame. But also there is, what if there isn't a free frame? Then I've got to do 2 more steps. Swap the page out and swap the page in. There's nothing free. So I've got to take a page out of memory and bring a page into memory. That's swap page, and that's very time consuming. In other words, the swapping in I'll always do. If it's a page fault, I'll have to swap in. But I may also have to swap out. And then I don't know what restart overhead means, why that's not called the page fault overhead, but then I got to restart the process, which means bring in the registers from memory. You know, there's the registers that I copied out. I copied out registers to memory. Now I got to bring them from memory back in.
Overhead is the time it takes to bring it back in.
I don't know what the difference between this overhead and that overhead is, but this is the restart overhead. How much time it takes me to restart the process. I got to restart the process because I stopped it and I let another process run. So that's how you're going to calculate. But the basic idea is that it's a percent times whenever I don't have to do all this page default, and a percent times when I do have to do this page default. So here we're going to example memory access time. Let's say the memory access time is 200 nanoseconds. That's this memory access time, right? That's in all things being good. Average page fault service time. Now it takes me 8 milliseconds to service a page fault. That's all. Look at what he just did. He just made your life a lot easier. He just said all this stuff together, page fault overhead, swapping in, swapping out, restarting, is 8 milliseconds. Milliseconds is thousandths of a second. Nanoseconds is, what's nanoseconds? Billions of a second. Because remember, in the middle, there's microseconds,
Which is a million?
which is millions. Micro is millions. You can check me, but I think I'm right. Nano is billions. So it's a little bit of a jump here. In other words, it's going to take you 200 nanoseconds, which is like nothing, 200 billionths of a second, to do a memory access. But it's going to take me 8 thousandths of a second to do a page fault. So let's say, well, we don't know what our P is. Let's assume any P in the world, okay? We're going to solve this in terms of P. So what is it? It's 1 minus P times 200. Remember, we'd like P to be 0. then this whole 8 milliseconds would go up. This is just for my own mental recollection, so that I can remember which is p, because p could be, which percent is the p? P is the one that how many times you have a page fault. So if it's very, very small, if it's all 0, then it's pretty much 200. So it's how many times, so it's 1 minus p times 8 milliseconds. Nikuda, that's the end of the story. That's the whole picture. Everyone sees that first line there? That's the whole equation. Now we're going to rewrite that equation as we're going to leave the 1.c, and we're going to say, well, let's put everything in nanoseconds because we have different, what do you call it? Frames of reference, different measures. One is milliseconds and one is nanoseconds. So 8 milliseconds is equal to 8 million nanoseconds because this is essentially 200 followed by 9 zeros, and this is 8 followed by, sorry, this is 200. This is 200 nanoseconds. This is a lot of nanoseconds. This is 8 million nanoseconds, right? That's 8.
Isn't a millisecond smaller than a nanosecond?
No, it's bigger. A millisecond is a huge amount. It's a millionth of a second. It's like not a million, a thousandth of a second. It's a thousandth of a second. This is a billionth of a second. It's a tiny, tiny amount. I want everything in those billionths of a second.
Millions in a million?
No, a million is 1,000.
Okay.
In Italian, mille is 1,000. Mille, you say mille lira. They don't have liras anymore. But there used to be a bill called a mille lira, 1,000 liras. They didn't.
How much is the?
They have that.
No, it doesn't exist now. It doesn't exist anymore. At that time,
It's crazy
There are
inflation.
liras
okay.
no, 500 lira. Mille lira was nothing. You had a coin of 500 lira, which was about $1. Like that.
You have liras in Turkey though.
In Turkey, yeah. But in Italy, I remember being in Italy before they had the euro, and I have a coin at home of a 500 lira coin, which is about, I don't know, $1, half a dollar, something like that.
Well, no wonder it doesn't exist anymore.
Weren't there liras at some point in Israel?
Yes, there were liras. Some people still use that word. Yes. Okay. People who want to sound old use liras and other terms. I forget the other terms. Okay. Anyway, we don't agree that you understand why we get this 8 million? Does anyone have a question about why we got this 8 million?
You're basically subtracting the zeros.
Well, maybe I said it wrong, but you need a lot. This line, the second line is in nanoseconds. 8 million nanoseconds is equal to 8,000 microseconds and 8 milliseconds. Does that make sense? This is how many nanoseconds. This is how I convert 8 milliseconds to nanoseconds. 8 milliseconds is a lot of nanoseconds. There was this woman, I never told you about her. Oh, I never told you about Grace Hopper. You know Grace Hopper?
Oh,
Oh,
you
you
know
mentioned.
assembly or something?
Yeah, I mentioned her in my lectures on assembly.
Yeah, the lab.
I mentioned her in the lab, I could be. So Grace Hopper she invented assembly language, yeah. She invented the concept of assembly language. She also invented the concept of compilers. Really amazing thing that one person would come up with both of those ideas. Although they're very similar ideas. Anyway, she would go around with wires in her hand to demonstrate. She would give lectures about she would talk about nanoseconds. She said the generals would be upset that they could take time they would send a message to the satellite, and then they wanted to have a satellite phone. The satellite phone was slow. And she said, but the generals said, but the light is traveling at the message is traveling at the speed of light. How come it takes so long? So she would have in her hand pieces of metal about this long. And she'd say, these are nanoseconds, like a bundle of them in her hand. These are nanoseconds. What does it mean? It means this is the distance that light travels in a nanosecond.
Oh, wow, that's cool.
There's that.
How did she measure that?
Well, we know how fast light goes. We can divide, just do division.
I'm saying.
Light
How
travels.
did they figure out how fast it travels in the first place?
How did they figure out how fast? They measured how fast light travels. This is actually an interesting question. Yes, it's empirically, first of all, one simple way, after they put the man on the moon, they put a mirror. One of the main things that they did was they
Did it
put,
send a laser?
they put a mirror on the moon and they sent a laser, they measured, so we know now how far away the moon is also much better, well, than they used it. But also you could measure either you know one or the other, but yeah, how long it takes to get there. If you know the distance, then you know how long it's gonna take. If you don't know the distance, but you know how fast light is, then you can measure how far away it is.
Right, either way.
Either way, you can't get both. But I don't know which one, but they put a mirror there. Maybe they were just trying to get the distance, but maybe, anyway, they measured, I don't know, physicists measured it. This is actually a big question because, Einstein says that you can't go past the speed of light. And this causes this whole theory of relativity. Because imagine if you had a flashlight, you're on a train traveling at the speed of light and you turned on a flashlight, would you see the light because the train is traveling towards you already at the speed of light? If I throw a ball forward on a car that's moving forward, then the ball will go faster than the car from the outside observer. If the car is going 60 miles an hour and I throw the ball 2 miles an hour, so the outside observer will see it going 62 miles an hour from where he's standing. The ball is going, to the car it's only going 2 miles an hour faster, but the ball, anyway, light doesn't work that way. But that's only because light's speed is constant, and yet then the question becomes who says light speed is constant? The answer is they measured it. It was actually, it's not everyone thinks that it's like a rule. It's not a rule. They observed it. How exactly they measured it, I don't know.
Yeah, it's just creative even to figure out how to measure that. Yeah.
But basically that's the idea. You send, you a stopwatch, you send a beam of light, very, very exact watch. Anyway, so everyone understands this second line here? 8 million nanoseconds, because nanoseconds are very small. So if I have 8 milliseconds, then it's going to be a lot of nanoseconds. Now, if I do the math here, I'm going to say 1 times 200 and negative p times 200. But this is negative 200p, and this is positive 8 million p. So if I subtract 200, negative 200p from 8 million, I'm going to get 7,999,800, because that 200 went away. And then I'm going to have left the 1 times 200. So it'll be 200 nanoseconds plus 7,999,000 p. So, okay. What do we see from that? We see from that every little p matters because it's being multiplied by 8 million. Essentially, we can round this off to 8 million. But in other words, so we're going to round this off to 8 million. Let's round this off to 8 million, okay? Everybody agrees that we can round that to 8.
What happened to the p that we subtracted everything?
Because this became negative 200p, and this became positive 8 million p.
Oh, okay.
So the p's just joined together. We got, essentially, we're rounding, then we're just going to say we're going to ignore this negative 200p. It just goes out of the equation. And we're left with 200 plus 8 million p. And that means that we have, now we say like this, if one access out of 1,000, not 1%, but 1/10 of 1% causes a page fault. So let's say like that, our page fault rate, our P is 0, 0, 1. Right, is that right? 0, 1 would be out of 100. 0, 0, 1 would be out of 1,000. So 0, 0, 1 is our P. So as we multiply this by 0, 0, 1, essentially we chop off these zeros, these 800, these last 3 digits go away. Essentially dividing it by 1,000. So we're left with 8,000. 8,000 plus 200. So that's 8,200. So we're left with 8,200 nanoseconds or 8.2 microseconds. So there we go. Everyone sees that? This math here is a little bit, I should improve this slide by putting some more steps in it. There's just a few steps that are missing, but this 1,000 drops off these 3 zeros, and then we're left with 8,000. And 8,200 nanoseconds, instead of writing, you could have just written EAT is 8,200 nanoseconds, and that would be correct. But instead he wrote it, he changed it again to microseconds, just to get rid of decimal points. So it's 8.2 microseconds is our, all because of our having, that's a slowdown by a factor of 40. In other words, if we wouldn't have had any page faults, we would have had a page fault rate of 0.2 microseconds, right? Just 0.2 microseconds. Now we have 8.2 microseconds. 0.2 times 40 apparently is 8.2. I don't know, is that right? Somebody have a calculator? He says it's a factor of 40. Let's see.
And slow down from what?
Let me just do the math. 0.2 times 40 equals 8. Yeah, about 40. It's a factor of 41, really, not 40. But
It's a fifth.
what?
It's a fifth, yeah, of 40.
Whatever. 0.2. Yeah, exactly. It's a fifth. So there's a slowdown of 40. What Zava asks, a 40, a factor slowdown of what? In comparison, if there be no page faults. If there would be no page faults, if page fault rate would be 0, then we'd be just left with our 200 that we were given as the memory access time. So this is another kind of question that could be on the exam. After all this theory, you know, he ends up just with a simple equation like this. What is the effective memory time if, what is the effective access time if memory access time is 200 and the average page fault rate is 1,000 and this is, you know, and this is the average. Notice he just gives you the average page fault service time. Thank goodness he gave us that. Because if he wouldn't give us that, if he would say all of these ones, then it would be more annoying. If he would say the swapping in is this, the swapping out is this, the restart is this, and the page fault overhead, whatever, is this. Or even the question could be even more complicated where somehow it's hidden in the information. You're supposed to figure out that there's a swap. But here it's just given. If I want a performance degradation, now here's the interesting question. We're asking the other way around now. This is also an interesting question to ask. If I want a performance degradation of less than 10%, in other words, this was not 10%, this was a huge percent. What percent was this? This was not 40%, 4,000%, right? This is a slowdown of 4,000%, because the percent divided by 0. If I want a degradation of less than 10%, that would mean instead of being a factor of 40 by a factor of 0.1, what would I need to do? So what would be the P in such a case? Now this math here is a little bit weird, because you never see equations like this with greater than signs. You usually see equal signs, right? But we're saying like this. What is this 220? 220, what's this 220? Somebody tell me what this 220 is. I know, I want to see if you can tell
Is
me.
it the 10% of 200?
Exactly. That is a factor of getting worse by 10%. Because it was 200 would be the normal amount. If it's 220, then that's 10% worse. So we're saying like this. We want our number to be less than 10%, less than 220. 220 is 10%. So how do we calculate our number? Again, it's 200 times this number times P. So we can now subtract. Why would we subtract? Because we're doing less than and greater than. If we're doing less than and greater than, then we just want absolute numbers, right? We just want absolute numbers. So we can subtract these milliseconds, these nanoseconds, from these nanoseconds, because we're just trying to get, we can subtract. So we're left with 20 nanoseconds, has to be greater than this number of nanoseconds times P. So we just divide. We divide 20 by 8 million, whatever, 8 million. And we get a quarter. We get 0.00000025. That means one page fault in every 400,000 memory accesses. That's our goal, he's saying. That's what we need to get. That's how good we have to be. That's how infrequently we have to do a page fault in order for our system not to be too slow. And actually, that's a realistic goal.
Is he switching between nano and milliseconds? Because I'm saying like 8 million divided by 20.
Is not that? How do you do it? Let's see. Well, let's do the exact number that he has there. What is it? 7,999,800 divided by 20 is not that. Maybe I did it. Maybe it's. Maybe I did the math. I did the math backwards. It's the other way around. Divide the other way. It's right. It's 20. Just do the math. You want to get p. So you have to divide both sides by that number. So 20 divided by 7,999,800, yeah, equals 2.5 times 10 to the minus 6. That's right. There's 6 here. 2.5. Put a decimal point here, and then there's 6 zeros. So yeah, you just divide.
Can I ask a question not related?
Yeah.
It's about Sunday. I don't know, it's just a general question. We have a final right after class on Sunday. I think.
We were the same day.
Same day,
Which Sunday?
like this coming Sunday.
Our advanced C class, we have an in-class exam.
Oh, yeah.
I don't know if this like works for everyone. Maybe we could have class after the final after. I don't know. You guys want to do that? That would work for me.
Or if you want, we could have a class on Monday. I don't know what you're doing Monday morning.
Oh, we have regular class on Monday.
You have other classes. And after that class, you don't have?
I don't know.
All right, so we'll do that. We can do it after. When is the exam?
At 12. Like
12 till 2, something like that?
2:30.
So, well, anyway, we're on Zoom, yeah?
Yeah.
Yeah.
All right, so we can have class at like 2:30. When are we finishing today? Another 4 minutes?
3 minutes.
3 minutes. So good. So any questions on this math? I'm trying to see what the next. Okay, so we'll stop here. We'll stop here with this nice math. And this is just to demonstrate the need for a good demand page algorithm and not to have too many page faults.